It's time to review our series and sequences here. So here we have a nice list of a flow chart of how to determine convergence or divergence using our series tests. So as we're looking at our series, remember some of these tests prove divergence and some will prove divergence and convergence. So some are easy in some situations, and some don't even apply to other situations. So, a quick review here. We're going to have first we have a test for divergence. That's to see does the limit equal 0 of the terms of a sub n. Well, if that's no, then there's no way it can diverge. It diverges. That's the nth term test right there. Okay. And then we can start looking at the form. Does it have a special form? Is it a p series form? 1 over into the p. Is that true? Yes. Well, then we can do the p series test. Is p greater than 1? Yes, converges. Nope, it's not greater than 1, it diverges. Okay, if it's not in that form, is it in the geometric series form? Well, if that's a times r to the n minus 1 there, or a times r to the n, it all depends kind of on the indice, what's going on for the summation, the index. So if that's yes, if the r value is greater than, or I'm sorry, less than 1 here, then yeah, if it's less than 1, then it does converge, all right? So it converges, and we know what it converges to. It converges to a over 1 minus r. If it's not less than 1, well, it diverges. All right, if it's not a p series and it's not a geometric, is it an alternating series? Does it have this negative 1 to the n or negative 1 to the n minus 1? If it's yes, then we can check to see if b sub n plus 1 is less than b sub n. In other words, if it's not increasing, it could be equal, that's okay. And is the limit going to 0 of b sub n? All right, now this note says b sub n, we take off the negative 1. We don't care about that. But is it going to 0? If so, hey, that's the alternating series test. Yes, it converges. If that's a no, for either of these, no, it doesn't pass the test. Now notice alternating series does not tell us divergence. All right, then we got a telescoping series. This is kind of a special one. Is it in that form? Are they alternating back and forth? Usually it looks like some form like the sum of 1 over something, whatever. I'll go a sub n minus 1 over b sub n. You know, usually it's in that form, all right? And that's alternating there because they'll cancel out. You need to write out some terms to see if they actually do. Okay, you might have to use partial fractions. Okay, but anyways, if it's clearly telescoping, we can see do the middle terms cancel out. If so, then we can ask ourselves, does that last term go to 0, all right? In other words, does it have a finite limit? So it'll be all the middle ones cancel, while the first one, and then the nth term. So as s goes to n, what is that nth term? All right, anyways, if so, we found it. If not, it diverges. All right, kind of a special case there. Now, Taylor series, we're not worried about that right now, okay? So this is coming up here, okay? Coming soon to a theater near you. So don't worry about that for this in between first little test we got coming up. How about the comparison test here? All right, so can we compare it to something? So if it doesn't match one of those special tests, we can see, all right, does it compare? So we find a b sub n, and if that b sub n is greater than the series we have, right? Notice we're talking about our series that we're looking at is a sub n. So if we can find one that's bigger, and if this one converges, okay, then we know that a sub n converges because this is the ceiling effect. If our new series b sub n, the one that we're comparing to, if it diverges and it is less than our series that we're considering, then it diverges. Okay, limit comparison. Well, that's where we take the limit of the ratio of the two there. If that limit of the ratio is a constant that is greater than 0, then if b sub n converges, then a sub n converges. If b sub n, our new one, converges, then, or diverges, then a sub n diverges. Okay, integral test. Well, we can make this an integral. If the integral converges, the infinite integral here, then our series converges or diverges. Ratio test. So the limit of the ratio of the two terms, the absolute value of the two terms. Okay, then that if that converges or not. Okay, then the root test. This is useful when we have a power of n. When we take the nth root, the limit as n goes to infinity of the nth root of a sub n. If that doesn't equal 1, then if it's less than 1, it converges. If it's greater than 1, it diverges. Because if it's equal to 1, it doesn't tell us anything. Same thing with the ratio test. If this ratio test is equal to 1, it doesn't tell us anything. All right. So kind of a big list there. But keep in mind, these are special forms. And these ones down here are kind of general techniques. All right, so there's a little summary of it all there. All right, let's practice some of it. So we started this whole thing with sequences. So if we look at this sequence here, 2, 4, 6, 8. All right, let's find a general term here. So the top is the even number, so that's 2 to the n. Remember, this is term 1, term 2, term 3, term 4. So that's n. And the bottom are the odd numbers, 2 to the n plus 1. All right, so now we can find the limit as n goes to infinity of 2 to the n over 2 to the n plus 1. Well, as we go to infinity, this 1 doesn't matter. Okay, we have the same degree on top and bottom, both first degree. So it's going to be the ratio, 2 over 2, which is 1. So yes, it has a limit. The limit is 1. How about these ones? 2, 4, 8, 16, 32. What's going on with those? Well, those are powers of 2. 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth. And then we have 1, 2, 6, 24, 120. Do you recognize these? These are our factorials. This is 1 factorial, 2 factorial, 3 factorial, 4 factorial. So this is n factorial. Now there's some clever ways to figure this out for the limits, but let's use one of our tools that we got with series, and that is the ratio test. And so the ratio test for series, if we consider this a series, 2 to the n, an infinite series over n factorial, well, the ratio test says the limit of a sub n plus 1, so that would be 2 n plus 1 over n plus 1 factorial, divided by our time, well, let's write it out for you. Okay, divided by 2 to the n over n factorial. Okay, well, that is the limit of 2 to the n plus 1 over n plus 1 factorial times the reciprocal, okay, to the n there. And with some canceling, we get this is the limit as n goes to infinity of, well, I'll subtract the powers here, n plus 1 minus n gives us 2 to the first. And n plus 1 of these will cancel. Actually, n of these will cancel with n of these, leaving n plus 1. There we go. And the bottom's going to go to infinity, and the top's staying at 2, so this is going to 0. So if the series goes to 0, so the limit as n goes to 0. The terms must go to 0. So series will only go to 0, because series is summation, if the individual terms disappear. Okay, so that's kind of a cool way to do that. And there we go. Okay. Little side note, you should have kind of a inclination that this goes to 0 here, because that top is growing, but the bottom is growing a lot faster. You can tell there. All right. So, all right, let's go to series here. So our nth term test proves some divergence here. So the limit as n goes to infinity of n cubed plus 1 over n squared. Well, we have a bigger on top. So anytime we have bigger on top, this is going to blow up. And so this limit goes to infinity, and therefore the series diverges. Okay, so again, this is in series test, it only proves divergence. Okay. How about this one? Well, what's the limit as n goes to infinity of sine square root of n, sine square root of n divided by the square root of n? So let's use the squeeze theorem here. Whenever we have a sine, a squeeze theorem is a good way to go here. So we know that this is less than the limit as n goes to infinity of the square root of n, 1. The biggest a sine can be is 1. The smallest it can be is the limit as n goes to infinity here as negative 1. How are we going to write this? Let's go negative 1 over square root of n. Okay? So, if we look at both of these, as n goes to infinity, this is going to 0, and this is going to 0 from the underside there. Okay? So that means that the sine of the square root of n over square root of n, that limit as n goes to infinity, is less than or equal to 0, less than or equal to 0. So by the squeeze theorem, the limit equals 0. Now, does that mean that this has the limit is 0? No, so that means the nth term test does not apply. Okay, so that doesn't tell us anything. Okay, so the nth term test is inconclusive. All right, so this is a good reminder that the nth term test only gives us divergence. All right, so let's practice using our calculator here. All right, so we can find the infinite sum. So use the summation key on your calculator. We're going to go menu, and we'll go to calculus, and we'll go to sum. So using our TI Inspire here, we can go plug these in, use the calculus, sum, and just decimals are great here. So you want to just use decimals. The fractions get kind of crazy. So using decimals, we get 0.5. We get 0. Let's go 3 decimal places. 458. We get 460. We get 4. We get 4.6. Looks like 460 again. Oh, look at that. 459,722, 459,697, 459,68. All right. So they're all going to about 0.460. And then down here we have the 10th one. And it looks like, we're 459,698 would be accurate to 6 decimal places. 459, 4, 6, 8. All right. So there's some partial sums, so we just can know we can do that. Now we're not worried about this at the moment. We'll look at that similar one with the alternating series test is what we'd have to prove there. See if that converges or not. All right, so and it's looking like the sum converges, right? Okay. Well, anyways, let's find the sum of these here. Notice this is a ratio test. I'm sorry, it's a geometric series. So we have a ratio to an nth power. So this is geometric. And we see that the ratio, which is 2/3, is less than 1. Okay, and therefore this converges. Since it converges, we can say what it converges to, because geometric series have a specific sum. So the sum is 1 over 1 minus r, which is, in this case, r is 2/3. So this is 1 over 1/3, which is 3. So it converges to 3. How about this one? Looks a little different here. Well, we could rewrite this. And let's see, if we peel this off, we can write this as 2 squared times 2 to the n over 3 to the n. And so this now can be written as 2 squared is 4 times 2/3 to the n. And now notice that we've got the same ratio here. So it's geometric. So the ratio is 2/3. And the sum, in this case, is going to be 4, because the a value is 4 over 1 minus 2/3, which will be 4 times 3, which will be 12. Okay, see how that works? Okay, so when we have when it looks like it's geometric, we can change it into that geometric form to find that. All right, how about this one? All right, this looks like it's telescoping, and it is. All right, so if we write this out to be sure of it, let's write out a few. We have plug in 1. We got 1 over 2 minus 1 over, plug in 1, we get 4. Plus, second term, plug in 2, we get 1/4. Plug in 2, we get 1/6. Okay, so that's the first term, second term, third term, we get 1/6. Whoops. 1/6, plug in 3. Plug in 3, we get 2 times 3 plus 2, which is 8, 1/8. Okay, and it's going to continue on. And we see that these middle terms are going to cancel out. Minus 6 plus a 6. Okay, so on and so forth. So the middle terms will all cancel out. So the question is, what's the limit as n goes to infinity of the last part? So this last term is what matters. The first term is 1/2. The last fraction, I should say, not really the last term. The last fraction, well, as n goes to infinity, this is going to blowing up on the bottom, so this is going to 0. So that last fraction is going to disappear. And so the limit, or the sum of the series, is 1/2. Okay, that's the infinite sum. So we can actually find the sum is the idea. Well, this looks like it's telescoping. In order to find that out, we got to use some partial fractions. So we say that 1 over n plus 1 times n plus 2 is equal to a over n plus 1 plus b over n plus 2, which is equal to a times n plus 2 plus b times n plus 1. Okay, we've done that quite a bit. We're just getting a common denominator here, and that's what we'll end up with. The common denominator is n plus 1 times n plus 2. All right, and so 1 has to equal the top there, n plus 2 plus b n plus 1. And now we're going to say if let n equal negative 2. And if n equals negative 2, we have 1 equals b times negative 1, which implies that b is negative 1. And if we let n equal negative 1, our equation becomes this part drops out, and we have 1 equals this. Plug in negative 1 for n, we have a times 1. So a is 1. All right, so moral of the story is this. Our series becomes n equals 1 to n of 1. So now we're going to plug in a and b to this. 1 over n plus 1. And the b value is minus 1 over n plus 2. You may have kind of suspected that. Again, let's write out a few terms here. So plug in 1. We have 1/2 minus 1/3. That's the first term. Plug in 2. We have 1/3 minus 1/4. Plug in 3. We have 1/4 minus 1/5. Dot, dot, dot. All right. So notice these are going to drop out. 1/3, 1/4, 1/5 will drop out, so on and so forth. So what's left over is the first term and wherever we stopped. So then again, we say the limit as n goes to infinity of the last term, n plus 2. Well, that's going to 0. So this last thing is going to disappear, and so all we're left with is the sum is 1/2. Okay? All right, so this has a specific sum. Yes, it converges and has a specific sum. So for geometric and telescoping, we can actually find the sum. Okay, we can't do that with most other functions. These are special just by the way they're made. All right, so we're going to look at series to see if they converge or not, but we won't be actually finding what they converge to right now. So let's look at those.